I have highlights from Chapter 9, so I took the slides, I summarized them. We have technical definitions. So a null hypothesis we already talked about, that tentative assumption. The alternative hypothesis is the opposite of the null hypothesis. What word do you see? Do you see sample statistic or population parameter? You're always going to write your null and your alternative hypothesis in terms of the population parameter. Right? So we have our sample data, but we're making assumptions and we're trying to infer things about the population. So some examples if you wanted it. So this idea is our alternative hypothesis is a research hypothesis. So we have a new teaching methods developed. It's believed to be better than the current method. So our alternative hypothesis is that the new teaching method is better. And the opposite of that is it's not better. It's no better than the old method. Okay? So if we were going to test this by using the average test score, how could I write this in symbols? Because you guys seemed to like symbols earlier. So if I'm going to talk about a mean, so this is the mean of my new method. Start this way. The mean of my new method and the mean of my old method. If one's better, that's what I did. I did it backwards. The alternative's on top. So the mean of the new method is better than the mean of the old method. And here the mean of the new is the same. Hasn't changed. So that's your option. Either one of those I would be happy with. You can say that it's just equal to, or you can say that it's less than or equal to. I'm good either way. Yes?
Is the null and alternative hypotheses the opposite? Like, is there a reason why I wanted alternative over one the null?
So the null is always the one that has the equal sign in it.
Okay. Right,
Does that help?
right, yeah. Okay.
Does that answer your question?
Yeah.
Okay. So the null is always the one with the equals in it. So let's try a different one. A new Salesforce bonus plan is developed in an attempt to increase sales. Kind of the same, actually that was kind of the same, right? The new bonus plan will increase sales, or the new won't increase sales. Sorry, I have that. I want to see the bonus plan. Oh, this one's more fun. A new drug is developed with the goal of lowering blood pressure more than the existing drug. Okay, so we have our alternative hypothesis and our null hypothesis. So again, let's assume that the way we're going to determine this is by using the means. Okay, so we have the mean of my new drug and the mean of my old drug. What symbol goes in my alternative hypothesis?
Less than.
What goes in with my null hypothesis? Or just either one. So by the new having a smaller amount, that's actually better than you want it to be lower. Right, so a greater than isn't always the symbol you want to use. Right, just to tell if they're different. So here, lowering blood pressure is actually a positive thing. Let's try something else. We can also do the null hypothesis as an assumption to be challenged. So here, the label in a soft drink bottle states that it contains 67 fluid ounces. Right? So we can say that the label is correct, or we can say the label is incorrect. And again, you can say the label is correct and just say that it's equal to, or you can say it's incorrect and say it's less than. You guys seem to be doing it. Any questions about this? You just got the board look, so we're going to move on. Okay. So here's some other examples for you guys to look at. We already talked about the idea of the one-tailed, two-tailed, and the directions that you can use. We talked about our type 1 and our type 2 errors. Here's the same picture again. We talked about confidence intervals, but did you know you could use confidence intervals to kind of do a hypothesis test? Yeah? No? Hadn't thought about it? So here, if I give you a confidence interval, and I give you the population mean, if the mean is inside my confidence interval, then I fail to reject my null hypothesis. My mean isn't different from what I predicted. But if my population mean isn't in my sample confidence interval, then I reject the null hypothesis and say, nope, they're not the same. Okay. So tying confidence intervals into hypothesis testing. We've already started talking about our p-value approach. And once again, you'll see the big thing, one of the big takeaways for today. If the p-value is less than or equal to our alpha level, then we're going to reject our null hypothesis. People always like having words to be associated with things. This is just if you need a word. When we talk about alpha levels, 0.05 is your common, that 95% confidence interval, that's your common. And then they do things by intervals, so you have 0.10, so 10% of the time. And you can go between 5 and 10% of the time, between 1 and 5% of the time, and less than 1% of the time. So less than 1% of the time, there's overwhelming evidence that we're going to reject our null hypothesis and conclude that our alternative is true. If we're between 1 and 5%, there's strong evidence. Between 5 and 10%, there's weak evidence. And generally, if it's over 10%, we're going to say there's insufficient evidence. So if you want a word, here's a slide. Oh, look. That look familiar? So the only thing different here is I added a step 0. You got to have that business problem first. Because you can't do step 6 if you don't have step 0. The test statistic. Right? I told you we're going to have a sample statistic. In this case, we actually have a population parameter. But we're looking at basically the difference between two means, and this is going to be our standard error. And basically, remember, all the standard error is, it's just your standard deviation, and it takes into account your sample size. We talked about that a couple weeks ago. Now again, you're not going to have to calculate this by hand, but you just kind of want to know what it is. And this idea is going to happen every time. So no matter what type of test we do, we're going to have a statistic subtracted from either a statistic or a parameter divided by some standard error. Okay. How we calculate the standard error is going to change, but the idea is pretty much the same. So I have some examples of where we're going to go through those 6 steps. We'll do one example, and if you guys want more, we will. So here, Metro EMS, Emergency Management System. So the response times for a random sample of 40 medical emergencies were tabulated. The sample mean, 13.25 minutes. The population standard deviation is believed to be 3.2 minutes. The EMS director wants to perform a hypothesis test with a 0.05 level of significance to determine whether the service goal of 12 minutes or less is being achieved. Okay. So all of those numbers are going to be used somewhere. So what is our, let's start with our alternative, well, let's do our null hypothesis. So what are we actually trying to figure out?
We're meeting our service goal.
Meeting our service goal, so 12 minutes or less. And so this is where, since it's or less, that equal sign makes it the null hypothesis. Okay? So the mean is going to be 12 minutes or less, which means the alternative is the opposite. Greater than 12 minutes. Everybody comfortable with that? Okay. They told us the alpha level is 0.05, that's step 2. Step 3, we don't have the real data, so we actually have to rely on our test statistic here. We have the sample mean of 13.25 minutes. We're saying 12 minutes is what we want to compare it to. We have a population standard deviation of 3.2 and a sample size of 40. So we do that calculation and we wind up with 2.47 as our test statistic. Given that test statistic, I can tell you that the p-value, when it comes from ISYS, is 0.0136. So why would I divide it by 2? Because it's a one-tailed test. Okay, so ISYS is going to give you p-values in terms of a two-tailed test. Okay, most statistical tests that you run are going to be two-tailed. Not always, but a lot of them are. So ISYS defaults to a two-tailed test. So you either need to go in and change the code to tell ISYS, I just want the p-value for a one-tailed test, or you can just take the p-value that you get and cut it in half. Questions about that?
Why? Can you just explain why this one's a one-tailed test?
Absolutely. That right there. So because we have a direction that we're looking at, that makes it a one-tailed test.
Okay, because it's not just equal or not equal.
Exactly.
Great, okay.
Yep. Perfect.
If the question had been worded whether we meet a service goal of 12 minutes, and there wasn't or less, then it would be two-tailed because it would be whether it's above or below.
Absolutely. So our p-value, once we cut it in half, is 0.0068. Our alpha level is 0.05. So if our p-value is less than our alpha level, I know I gave it away, but what do? We reject our null hypothesis. So that says, it's not this, it's this.
Could you draw like the curve?
Absolutely.
To show that?
So what we're doing, we're assuming it's a normal distribution. Our sample size is bigger than 30, so we can make that assumption pretty well. Here's my mean of 12. I'm interested in 12 minutes or less, so I'm kind of looking this way. I've got a p-value of so this little area right here. So ISYS gave me these two areas for a total of 0.0136. I'm not interested in this one, so I cut it out, so that's why I'm dividing by 2. So this area right there is 0.0068. I said I would be happy if the entire probability was 0.05 or less. And it's actually less than that, so it's in my happy region. And since our p-value, if it's our p-value, the probability of this happening is less than 0.05, we're going to reject our null hypothesis.
So you're saying that there's like a 600s or thousandths chance that we'll meet our service goal in 12 minutes?
Mm-hmm. Because remember, our sample is actually up here.
Yeah.
So the EMS director's not happy, but you're happy just because.
Well, so this is like the crazy question. So some people, like, your assumption, like everybody's like, oh, I rejected my null hypothesis. This is great. But in this case, rejecting your null hypothesis sucks, right? Because you're not meeting your goal. Okay. We're going to have an assumption, so we'll test to see if things are normally distributed or not. And the null hypothesis is that it is normally distributed. The alternative is that it's not normally distributed. So for us, when we do that test, we don't want to reject our null hypothesis. So rejecting your null hypothesis is not always what you really want. Yes?
So what's the point of doing all this if you knew at the beginning your sample mean was greater than your goal? Why did you do it?
So it is bigger, but is it statistically different?
Significant.
Right. So yes, so this sample we looked at 40 different emergencies. It was 13.25 minutes, but is that really statistically significant from 12? Right? So I mean, when we're talking, here's our goal of 12 minutes, but we're making it in 13. Is 1 minute statistically significant? And in this case, yeah, it is. So if I was going to go back and tell the head of the EMS what I would say, oh, here's the picture for you.
Yeah.
There you go. But I like drawing anyway. So if you go back, like, we don't have enough statistical evidence to say that it's not meeting its response goal. Oh man, I hate when I have to think again. I'm on cold medicine. This is not helping right now. So there's sufficient statistical evidence to infer that Metro EMS is not meeting the response goal of 12 minutes.
Right.
Okay, we're good.
Yeah.
Just right there. So everybody's happy with that? And that's what you could go back and tell them. It's like, nah, you guys, there's enough evidence that says no, you're not meeting that 12 minutes or less.
But then if the p-value then like 0.06 or something,
Right.
then it would have fallen on the
other side.
and then we would fail the rejection.
Yes. Questions, comments? All right, let's skip ahead to a couple things. So we can do the same thing with proportions. The setup's the same thing. We still have a test statistic, we still have that population parameter, and we're still having some type of standard error that we're looking at.